Welcome back, everybody. It's been a few months, but we're finally at a point in Seraph development we're showing. Recently had enough real life interest to actually start making this video. Here I'll pull up the GitHub, and this is the GitHub for the project. I'll give a disclaimer that this version is behind the actual nightly build, which can be found on the Discord, just because GitHub was taking all the code and training regardless of your settings or whatever. So moved everything off of GitHub. This was last updated 2 months ago. So for the actual nightly build in the version without the obvious landmines, that can be found on the Discord. So I kind of want to address the current field and specifically some of the current claims, like Dario Amodei, when he was before Congress, claiming that open source models are dangerous, that it's impossible to know what's going inside of a model, only they know what's happening, which is purely outrageous. And recently, with the research releases from the research at Anthropic, it's kind of apparent to anyone who's been working with the transformer and understands how transformers work for a long time that they're just now starting to understand their systems. And they're applying a lot of the same principles we've known, just at scale. Most recent offender was the J-space paper. They talk about the model's internal representation of its space, and they're anthropomorphizing that. When, if you know anything about transformers, we've known about the internal space for a while. And in fact, about a week or two before they released their paper, there's this other video I came across randomly by Chris Hay, where he does the exact same thing, just an open source guy doing the exact same, showing you exactly what's inside the models at each layers, etc. So it is quite apparent that Anthropic and all the companies are like sharks in the water. They're very afraid of what's happening, where the open source is going, and China is very quickly creeping up on them. Address a few things. So a lot of the performance and stuff has been like, this is all non-relevant anymore because changed absolutely a lot. This original version was the naive version. I mostly wrote it. If you can see the plot code conversations, you would see me honestly telling them not to mess with the math, stuff like that. So this version has some issues, say with the tokenizer, etc. But the nightly build has all the fixes. And one of the biggest things that you find is that the transformer, or the principle behind the transformer, was the pinnacle of computer science, right? And the goal was to get a program that could take in any arbitrary amount of data and then use it, right? Whether you're taking time series data, whether you're taking your graphs, whether you're taking language data or NLP, or you're taking images, right? You can rearrange the transformer and get it to understand different types of data formats. So this was the holy grail, right? A program that could self-generate new programs. And I don't think it should be locked behind corporate walls, and it shouldn't be locked behind the guise of dangerous research. All right. So this will be broken up into 5 sections. This is the intro. We'll have the part 1, which is the engine and the dashboards. We'll have part 2, which is topology. Part 3, which is initialization. And part 4, tokenization. Part 5, which will be the results and the closing. All right. Okay, let's dive in. This video will take place primarily in the terminal. So we have our desktop, our black box, no distractions. All right. We'll set her up. We'll set up our workspace. There we go. We have a terminal. I use KittyTerm because it has the built-in multiplexer, has the built-in tabs, very keyboard friendly. So we'll head to Seraph. That's the project. See the structure. We're going to pop into Ranger so you can get a better view. And you can see the directory structure contains the include directory, the shaders directory, which contains all the shaders, the source with all the source files, tests, and peripheral tools such as converters, monitors, vision system, and then the GPU viz, which we'll get into in this video. We can compare to the original version, which is the one I primarily wrote up, and we'll do the same thing, and you can compare the difference to see that the complexity has greatly increased. And you see most of this was done with CPU stuff. So as you can see in the test directory, a lot of it has the AVX and CPU stuff, which is what I was more familiar with. And this version now has the Vulkan and all the CUDA as well. You see the comparison. The tools dir was mostly around stuff for finding and dealing with all that stuff. Shaders too, and you can see a bunch of not much, but size differences as well. Okay. So come here and you can look at the sizes, and that pretty much nothing is over 300 kilobytes. They're trained because it's bundled with the dependencies, and see that they're absolutely tiny because a lot of them are statically linked. The ones that cannot be are ones that have external dependencies such as Vulkan or CUDA. When we go to the tools dir, we can as well see size as well for all converters and everything, absolutely tiny. And then video inference stuff has increased size just because of requiring STB image. But the entire goal is to fit everything within 8 megabytes because a lot of microcontrollers have 8 megabytes of PS flash RAM. So the ability to fit the entire bootloader and everything you need to turn on the CPU, as well as an entire engine for training. So go. We'll run one of the binaries such as Seraph train. So you can see the outputs. So those are the options to give. So we'll head over to the CUDA device, and we'll head to Seraph, and I'll show the output for Seraph train CUDA. And you can see they're very similar. Pretty much can run all of the actual standard training exactly the same. One with CUDA dependencies, and this one specifically has profiling. It allows you to profile the NVIDIA GPUs. That's where you get the profile logs, which I'll show in a second. You can, but the Vulkan timing is a little different when you're not using their direct API. So you can profile, isn't as accurate as NVIDIA's profile just because NVIDIA comes with one. But this also has all the video stuff as well, which the CUDA has not been ported over. So those are kind of the two things. If we now show you the monitors, and we're going to start going from back to forward. That way you can see all the stuff that interacts with the system so you can get an understanding of all of interacting with models. And then we'll go into initialization, and it will make sense in the order. Okay. So the first tool is the GPU visualizer. So it is the Seraph GPU Viz, which is a server that launches all the HTMLs and launches all of that stuff. So here, let me pull it up. All right. So here is a tool. Has the ability to launch training from a web browser if you're not so much a terminal. I prefer the terminal, so it is just a kind of quick way to just throw it out there. They give all of the parameters you need, lower fine tuning, your checkpointing, all that stuff. And I had somebody ask about this. So Tetyah self-generated this a while ago, and I liked it. And then after I made this tool, I was like, this is the perfect one to put there. And I think it fits. So all you can do is you can load your GPU. So this will run the query tool and give you information for your GPU. And we'll give you the stream multiprocessors, your warps, your threads, etc. and we'll give you your computes and everything. If there is a model, right, you can set the model path. So let's set just the base model, and we load this. It pulls the configuration and then gives out the optimal sizings, right? So we'll load a profile log. Hide this one. This was an experiment. This was like a LoRa trained one, so isn't that big of a model. We'll let it load up. And you can see we have our entire profile down here. We'll click on this one, and you can see the actual operation. You see the matrix. You can see the multiplication against the K matrix, which is the embedding model embed layers. You have your actual grid size, your block, number of blocks required for this, and the blocks per SM. Got threads and the amount of waves it took, timing, and the percent. So here you can see the actual percentage breakdown here. So take this. And the colors coordinate to each SM. So for each SM is given an entire tile. Right? And it's not, you can see right there, is quite a lot. You have your different operations like your attention, and you can see it's actually built out like the attention network is. You can see operations, right? The ones like the atom. And you can see by the layout the type of operation it is, right? Their linear operation. Because they take an entire block, right? Remember, each stream multiplies is a red, orange, yellow. Corresponds to sync one of these. You can zoom in and find, say, something like your RMS, or that's an add. There you go. Your RMS, right? You can see pretty much everything you need. If you're ever running it from here, that's what this terminal is. It'll print out all the profile information you need and everything. So that's the tool. That is for looking at your GPU and everything necessary to train, optimize all of the math and the operations. Okay. And this model was actually not the 540 model. That's just the model I set. So you can set a model for training, but this model was a 528 model, which was that Claude model. And you can tell by the actual matrix, which is the embedding dimensions. Okay. So the second tool is going to be the band monitor, which allows you to take the bands of any model. So we can actually load log files. So here, checkpoints, graphs. We'll load a log file. Okay. And then we'll also load the graph that corresponds to that. Checkpoints. Here we go. And there we go. You got a baseline log and the baseline. This isn't very much helpful, right? There's not much information. So if we actually load a model, right? So we go to models, and we'll just load the config.json for this model, just what it belongs to. And then we reload the log. Here we go. Reload. Oh, I guess you guys can't see the actual thing opening. So here we load the log. Load the log, and then you get the actual summary information for the operation that ran for that training run. And if you see here, all right, tells you which bands, walls, how long it's spent there, the delta loss, the absorption rate, and the resistance. Okay. So keep this in mind for walls and bands, right? Because I'll explain that in section 2. But you have the ability to see your entire training operation and where your model had problems. And those walls and bands are the loss walls and the loss plateaus in the training run. Okay. These are pre-predictive, by the way. So if you load another graph of the actual trained model, I'm pretty sure this is the one where we were intentionally trying to create the model to overfit. Yeah, see, there you go. This is an actual model, and this is a horribly overfit model, right? This is what I'm trying to train it on Claude, where I was like, we want to overfit the model just to see if it'll learn anything. And as you can see, the model begins to very quickly drift after. So that's the band monitor, gives the ability to see your logs, your actual log files, see your ability to see all of that. The next one is the tensor viewer. And the tensor viewer gives the ability to view the tensors in the insides of a model. So if we go in your checkpoints and say we load a micro model, actually we'll go into models. As you actually load the base untrained model, we can here get the internals of the model. We can see the entire layers by matrix, by name. Okay, we can see the distribution, right? Standard deviation, everything. As you can see, everything's kind of flat, a lot of static, no structure at all. Okay. So if we compare, we can compare to a actually trained model. So downloaded Win3 to test. We'll load up the model at save tensors. It's a little larger, about 1.5 gigabytes. So take a second to load. And there you go. We can compare all of the layers and accurately see them. Like this is a 1x54, so this is a linear layer. But as you can see, the difference between a trained model is we have actual structure. We have actual values, right? There's actual places of higher and lower distribution. So we can change it to, I think diverging might be better. Not so much. Plasma definitely gives it a little bit more. So you can see a lot more higher end structure. You can see the means are pretty zeroed compared to this, right? Compared to a completely static model. AC comparison. So you also have the ability to profile. So if you can load an entire directory of tensors, come here, checkpoints. Where did I run it? I ran a test on one of them. I think this might be it. Yeah, this was the LoRa fine tuning. But you have the complete ability to look inside the model, get the actual per matrix numbers, and see the entire internals of the model. All right, so this is for a trained model information. So now that we have the visualizations from being able to see your hardware, being able to see the model, and being able to see the training dynamics, so the interconnection of them both, what we need is an actual model. We have to get a physical model on disk. So if we go in the models, and we can save tensors, right? So we can tell it to strings, pull out the strings from the model and save tensors, and we're gonna look for the metadata tag. All right, I got an old keyboard. That's the reason it's doing this. All right, metadata, okay? And here we go. We have the entire metadata printed out, okay, of the actual model. Okay, this isn't very useful, is it? So what we're gonna do is we are going to you're always gonna ignore that. All right. We're going to grep for that, and we're going to put it through JQ so it's actually readable. And here we go. We have our shapes, data offsets, right? And if we come back up here, this was what's in the file, and this is what it looks like. We have a format. I kept it as PT, which actually stands for physical tensor, since that is the format of Tetyah, but it's compatible with PyTorch, which is convenient. Xavier random has the rope layout of interleaved. And you can see by the shape, 12096 was the configuration of this model. And then you have your exact data offset from 0 there. The self-attention projection layer starts where that ends, and ends at the multiplication of this. Next layer as well. So you have direct data offset for where every tensor is, and you have a physical model. Okay. Everything in the model, every definition corresponds to the actual offset of the actual model. Okay. And that is what the physical model format is. Take it to Pickle, which has all of the extra metadata. Take it to Hugging Face Safe Tensors, the base Safe Tensors format, right? Everything that your computer needs, everything that you need is all fit in just the data file, all right? And I think that is where we're going to end this section, and very good. Okay, so we just went through how to inspect and look inside the model. All right, and we have the physical model safe tensors. Right, but the question arrives at, where do these magic numbers come from? Okay, you take numbers from a config and you get matrices out of it. Right, where is this actually coming from? Well, science is about prediction. Okay, and the ability to predict what will happen is the ability to understand what will happen. Okay, so here is the actual Desmos topology graph, and this is the actual equations and where everything comes from. Now we talk about the head dimension and everything. We set that by z, and I'll go into this much deeper in Patreon and with full dedicated video. That's kind of what's been taking up a lot of the time, is breaking down all the different parts of this. But consider we have the head dimension, we have the number of heads, the hidden size, the learning rate, all the FFN projections, all of that, normalizations, attentions, and all the equations, whatever. So we'll dive deeper into this, but I'm going to show you something that, take this, the sphere is the RMS norm sphere, the root mean square norm sphere, which bounds all of the actual points and the gradients within the actual model and equations. So that shows that this internal this is the area of distribution for when we Xavier randomly initialize. This is the area for random distribution. Okay, yeah, so that's a little bit easier to see. Okay, let's actually reduce these all. Okay, so reduce. Okay, so then we're left with rope, and actually we'll take this off for a second as well. Okay, so when we're left with a topology of just x, y, and z, right? We're left with a space of which we want to initialize some amount of information, some amount of data. The hidden size comes from this, and this determines a lot of stuff that depend on it, but is almost completely based on containing the model and on setting a maximum for the value of the model. So here, we'll take this. So you have your entire model here. We'll activate the rope, and this is one of the biggest things to pay attention to. And again, like I said, I'll go deeper into it. The rotation positional embedding is these pedals, right? Pedal geometry, right? Where it is a sine wave that goes off from the center. And it's a multiplication of the head dim, which is h, times theta, which is an angle, okay? So you get the number, or the hidden size, times the head dimension, times the head dimension, or the sine waves of the head dimension times its angle. And you get this. Now I want to show you something interesting. People say, oh, does increasing the hidden size affect any of those? Does increasing this or that do that? We can actually watch it and see that increasing z itself holds almost no effect, holds no effect on the heads, holds no effect on rope. It increases the area of which each head has to attend to, but even at 1024, there's been no effective change to the actual heads. And the heads are representative and are what take in the attention. So we'll reduce this again. But now, I have the sine and the cosine. But now, what happens when we increase the number of heads, right? So we'll actually do this by 9, 8, right? We see that. So what happens when we these all up? This one is half the heads times h theta. This one is a quarter, right? Let's put all of these in. And let's change the head and watch how quickly the internal representation space changes. We're only at 16, right? How about 12? We're only double. And look at the apparent complexity that occurs from giving the model more of an ability to cover space. As you can see, these are all the spaces taken up, okay? So by changing the number of heads, you can change the amount that the model is attending to. That might be known, but you can see the actual complexity here. And here I will play the actual form, right? And this is one of the reasons why it is when people say, oh, we're just going to give something so that we can simplify it, it nearly has no ability to convey the strict complexity, right? Comparing this to this, okay? And the changes in this are astronomical. It's not very hard to understand, but the actual change is much larger, okay? Now, what we talk about when we talk about walls, okay? So this is every place where the model can attend to and can pay attention to any dot that is inside of its space. If we take loss, the optimizer, we can actually put everything back in now. Got it. If we here come in, all right, this is a very brief overview. So if anyone who wants more information or wants to go a deeper dive, more will be on the Patreon. But what is meant by petal walls? What is meant by loss rings? Right? Is we do not believe in heuristics. Okay, these are actual petal geometry. Right? Sine and cosine wave and angle. Right? Bound within a sphere or in a circle. Okay. So what do we mean by loss plateaus, loss rings, etc.? We're defining the points at which the loss function, okay, for this model dimension, where each head crosses the loss plateau, okay? And at every point it crosses is a point where the model has to integrate those findings into the larger sphere. Okay, so you can see there's one here. There's another one here at 5.2. There's one here at 4.7. Another here at 7.4, right, etc. There's a large gap. There's one here at 3.6. And then we have a massive gap. This isn't actually part of the rope. This is one of the attention. A massive gap. And you can see the attention pierces through this gap. But until the next head isn't down here until 2.4. And again, all the way down again till here. Okay. So intuition might get you to understand, but it's not going to tell you that in between the model paying attention or learning this band, this frequency band, and then learning this frequency band, there's nothing for it to learn, and it is held by attention. That's where the attention mechanism comes in. And here is a kind of, here's the animation that I made that goes with this, right? At Z540, the length of Z is equal to 6.29. That's the maximum loss value. And at each place, the model must integrate. There's that large space, and it must integrate all of those spaces in. Now, the way to do this is through warp shuffling, which is a natural tree reduction that GPUs and CPUs or GPUs naturally use. Okay, so in order for a model to learn, it must descend the bands, right, accurately. Okay, and the bands are not in this format that we see as this singular line, but are in a rotation space. So it is not that the model has to fall lower. It is that the model has to navigate the space. And when you see it being bounced back, your intuition goes, oh, it's being bounced out vertically, right? In comparison to this, you would say, oh, it went down and went back up, right? But in reality, it is being pushed back into the center, right? Like any type of field is being pushed back in because it does not contain the necessary momentum or anything to escape. And once it has reached the final, its 0 point is at the exit or at the bounds of the actual RMS norm sphere. Okay. So we have that there. Right. And this is just a brief, very brief overview of the topology. So all of our numbers right here come from it. So here we have our topology, right? And if we go into the models, if we cap the config, or actually, I don't know, the config, we can see the actual numbers, right? 96 for the vocab size, hidden size 540, hidden layers, intermediate size. And the intermediate size is somewhat arbitrary, but it determines the attention focal point. As you can see, massive. It determines the attention focal point, which is the maximum point here, right? At z is z. So that is where this appears, right? And you can see the FFN projection here. And again, we explain all that in the Patreon video, right? And that'll be the end of this section. So we go from topology, right? We go from numbers, we go from the actual math, the actual space, layer space, and before our model has touched a single electronic system, we already have the entire topology predetermined, pre-predicted. We have the entire training dynamic pre-predicted. This is where the mag loss is going to be. These are where we're going to find resistance, and this is where the model is going to have issues. If there is any issues in the actual training run, these are where the plateau should be, pre-predictive. And as you saw in the baseline log from earlier, that is where the pre-predictive layers are going to be. And that will be the end of this section. All right. So now we have our topology, ways to observe it, pre-predictions, and we can take a computation device and we can place our physical model on it. And in the last video, I showed how to query and interrogate your system to find out what it's capable of, all of your flags. Right? Be able to see how much memory you've got, right? So we'll take a deeper dive in Patreon, but we have our device. It's ready to initialize a brand new model and ready to train. So the tool we use will be Seraph init, which can initialize the model using only a config.json. So all you have to specify is config.json. There's no complexity, and we'll open that config just to show you, right? Model type just tells the engine what model, architecture. You have all your information. So we got all the information from from Desmos and our topology. You put it all here. Basically, beginning of sentence, end of sentence, and pad for any empty IDs. And then you have optional metadata that you want. So we can actually delete all of that. And you can see it's 20 lines. That's all you have to understand to be able to create a model with this engine. So actually, no, we're not going to save that. So let's start with there in it. And in fact, let's delete the tokenizer and the vocab.json and just give ourselves the vocab.txt. rm. Boom. So now we have a vocab.txt. And if you look at the help output from Seraph init, you'll see that it takes a config, or you can pass it a vocab, or you can use build, which will build it directly from a dataset. So let's actually run this on this directory. So Seraph init, this directory. So this is, and we'll set it to model users, right? And this is going to take that vocab.txt and generate everything we need. Okay. So we have the models loaded, builds the tokenizer. This is a word level. Generates the embedding weights, so it generates the actual matrices that we defined. Here the total tensors, the size, and now you have a physical model, right? And we can strings model data into HQ. And there we go. You can see now this is an uninitialized model. Okay. There we go. You look, now we have the tokenizer JSON and the vocab.json. Now the vocab.txt is nothing more than a list of words. Just an entire list of words, and a serialization is the line number, right? And then that gets built into a JSON. It's easily serializable. Can pad beginning of sentence, end of sentence. Okay. So now we have that. It supports the byte parent coding algorithm as well as the word level algorithm and the morpheme aware algorithm, or MAW, which is the one that I developed for natural language processing. It's still taking time and experimenting with that. So we're just going to init this model with a pre-made vocab.txt from a parent model. And if we want to, say you don't have vocab.txt, say you only have a data set, we can also run the build command against a data set. So if we go to dataset stir, let's do something like GPT shard 0 JSON-L, right? 1, 2, 3, 4, 5 zeros. So Seraph init. Let's remove the model, the tokenizer, and all vocabs, right? So we are left with nothing but a config.json. Let's do Seraph init. Here, model the save tensors. We'll do -- build, and we'll set it to data sets GPT / shard 5.json. Okay. Let's see if I built that. Seraph vocab. Oh, I got to do it from here. So we got tool Seraph init. Let's actually specify models. And we'll do tensors. And there you go. Because it looks for it from the home directory. Now the shard 0 JSON-L is, I think, a few gigabytes. There we go. And as you can see here, derives a vocab, gives you your unique words, vocab budget, and tells you what your coverage is. Okay. So the model only has 12,000 words and fits with no extra words, but 11,000 is only enough really to cover 88%. Okay. So that is the issue with word level. If you ever heard it, like why we changed to the byte parent coding algorithm is because word level is one single word per ID. So if there are words that do not show up, then the model will not learn, or will have to kind of guess on new words. And you can see it does everything. And if you look in here, there we go. We have everything we need. Okay. And we can revalidate. You can revalidate the model. There we go. Perfect. And that is how Seraph init works, right? And here is a animation. You just take that config and it reads it, pulls out the layers, and sets them up. Using that, what I showed from the Desmos, that less than z squared, to maintain inside of that ring. Okay. And the final thing I'm going to show is the dataset viewer. Okay. Now this allows you to file. Oh yeah, I forgot you guys can't see that. So we'll open a data set. We'll actually open up that GPT-2 climax and let it load. And here you go. This is just a wall of text data set. So it's just wall of text. If we open up another data set, say here is a conversation log. Here we go, 90C. Let's see if this one's useful. Yep. So you can see here, this is just a simple conversation I had where I was like, I need to sync everything up. But you can see we have our tool use, the tool calls for thinking, everything. And this is all from my own data, right? So this is my conversation with Claude. There's not been any synthetic anything. So I have all the right to this information. Anthropic does not actually have the right to train on any of this information. So this is what I'm showing you guys here. Okay. So that is a way to view it. We can actually open up a CSV, and I'll show you what a CSV looks like using the Dolly 515K LoRa data set. And you can see here, like this. And it opens up a little bar to actually read it, but you guys can't see it because the screen share doesn't cover that. But you just hover over it and it shows the full text. All right, perfect. So that is where you can edit your data sets. You can manage your data set. You can look at what's good and what's bad and do it like that. All right. And next will be tokenization, and we'll kick off training. All right. So you're in part 4. We'll do the Seraph tokenized walkthrough. Let's recap. So we went from absolutely nothing, from just an idea to math and Desmos to a scientific prediction, and then a physical model only coming from a config.json. Use the parent vocab.txt. What? From there, we have everything we need to actually train. But we needed some data. So you have your data sets. You can get them off of Hugging Face. You can get your LoRa data sets. You can create your own data sets using sensor fusion and different sensors like I did. You can create your own versions based off of conversations, or you can use the raw conversations from any models like Claude or GPT as they are your property. So as you can see here, we're missing training data or tokenized data. So all we have to do is go and make some. So let's actually, do I still have the, let's see if the output, no, we don't. All right, cool. So the merge datasets optimization is simply just a tool that's going to merge all of it. So if you hit that, you can see it takes output directory. So it'll be from here, it's that data. Oh my gosh, fat fingers. And we are going to send it the directory. So that's and boom, we now have a file. And there it is. It exists. Next thing we're going to do is we are going to tokenize it using Seraph tokenize. Okay. So Seraph tokenize. And all it does is it takes a model, takes the input JSON. We'll do a Seraph tokenize. Takes an input JSON and brings out the output Tetyah. So specify the model, which will be the model you had. And we'll do train. And there we go. And there's everything we need to train a model from scratch, all starting from just a config.json. Okay, so we're actually going to train on 2 different types. Okay, so on this, I will launch this in a second because it uses up the GPU. It made us withdraw the GPU. So I'll have to pause the video. But we can go to the CUDA device. Okay, and then you can see a lot of the vision work on that that device. So remove the token. You don't see the tokenizer config as well, which is a Hugging Face thing. So you can add those if you want to compatible with Hugging Face or whatever. We'll take, let's see, the data sets here. We'll take the shard JSON-L because this is part of the GB2 climb mix. Just random wall of text ones I showed earlier. So we'll just run the same exact command. Seraph, tokenize, datasets, shard, and then the output is going to be model/train. Sorry, specify the model. All right, hold up. Models. And then we'll do models. And look at that. Serialized 52 million lines, 50 million tokens, 86,000 samples. That's a lot. So we have a model ready. And actually, let me verify to you all that this is a random model. All right. Hello, how are you? Organization debate constant. It's just random. Shows the same behavior as the previous one. Yeah, and garbage. And you see the random distribution. So these aren't the exact same model. See, this one has the same issues. It's just spitting out whatever words it knows. All right. Okay. That was just a sleep timer. So here we have everything set up to train our model. And now we're going to actually launch training. So we can launch the CUDA binary. Make all those. Dash. Or we'll take takes model. Takes a model, takes a train token, and then takes any of these options. CUDA models and model/train token. We want full training. Since this is a randomly initialized model, we'll set it to 1 epoch, so we're not spending forever. Learning rate. And once again, the reason these are so small is because we can scale at any point. We can copy another model architecture. We can do whatever we want and get out a working chatbot. The goal is to create models that can be compressed down at the pre-training level, right? And we can experiment upon the pre-training. And at any point you want, like I have access to an A100, but I'm showing you on I think it's a 3090 and an AMD iGPU. So at any point, you can just hop on a bigger device or whatever, right? Bigger model, whatever you need. But we're taking these as tiny models and finding out how to make absolutely micro models extremely powerful. So we'll run 1 epoch so you see the model learns to see how the logic distribution, everything. We're going to set there's 80,000, so we'll log every 10. We'll save every, let's say, 30,000. That way we only save 3 intermediate checkpoints. We'll snapshot every 10,000. And we will checkpoints /YouTube. Okay. Or YouTube. We'll run like that. I'll actually just to show you. Okay. And that's pretty much all you need. Tell it what type of training you want, your learning rate, which is topology derived, your log, your save, intermediates in case something crashes, snapshots whenever you want your gradient field snapshots, and your checkpoint. All right. And I'm going to run this just to show you for a little bit, just to show you the speeds, and then we'll run it for real. Yeah. We're sitting about what, 2,000, 2,700 tokens per second. Okay. Cancel that. And we can add more. So you have flash retention. And now we're sitting at around 35, give or take. We can also do BIA16 to make sure the weights are not in FP32. And now we're sitting at 5,000. So there's a lot of ways to increase the speed. We can even batch. We can batch. And you can see, right? Q. Oh. And we can force the gradient accumulation as well. Right? And then almost hitting 6,000, right? So we're already beating PyTorch. We're already beating all the naive implementations. Okay. So I'm going to run these without any of these so that you all can see. And in fact, I'm going to remove and then we'll run it from scratch so that nothing is messed up. Now, the primary reason I want to do this is to show you all this. So we're on this computer, or we're logged into this device. We go to Seraph, and we look at checkpoints. We find the YouTube vid checkpoint. All right. This is where the monitors come in. Okay. And in fact, we will do this. And in fact, we'll take Seraph. Control %. And you can see we're still healthy. Naive is running. All right. And then we're going to do Seraph dash topology. Okay. To give us the topology. What we're going to do is tail and +1 darkroom rights. And then we're going to do the checkpoints YouTube/train.log. So we'll send that through and we're going to pipe that into Seraph topology model and we'll tell it the model that it belongs to. And here we go. We'll do the same thing here. Tail plus and tail and 1 f check /u flash. And I'm just log. We're going to pipe that into Seraph and the band monitor. So this is the actual tool that the dashboard I showed earlier gives you. So this is the Seraph band monitor, and we'll tell it as well. That's the model. And here we are. We can watch the model descend. Okay. We can watch the dynamics. We have a here. Let me zoom out. There you go. And now we are just sampling the actual distribution of the physical model, the actual data offsets, randomized, initialized numbers, right, from the actual model. And we can watch it. And we know that when I was talking about the bands, the length of Z earlier from Desmos, these are all the bands. And this tells you how long it sits in a band. And right now we're waiting for it to drop its loss low enough to actually enter the topology. So the model has not even yet entered the topology until it hits the length, which is 6.24, which is the one for 540. And here we are with everything we need to watch, and we can step away. This does not interfere with the GPU at all because these are all CPU and they're all in C. And you can see here, we haven't lost any speed. We're sitting at 3,000 and we're still watching it move step by step. All right. This might take about an hour and a half. So we'll pause the video I will run the model on the iGPU and then we'll copy it over and get it done. All right. So there, train models, training to 1. Oh my gosh. 4, and then we'll do 4. And this one, I remember it had 4,000, I think. So let's do a few epochs. Let's do like 3 epochs. Right through 1, 5, 1, 4. Do log every 10. Every, and then YouTube, and I think there's one thing, snapshot. So we're going to snapshot much more frequently with this one, so you can all see what an actual long snapshot looks like. All right. So we'll hit this, and I'll see you guys in a sec. All right. So training is finished, and we have the timing. It took a little bit, and so have CUDA finished. I copied it over to this device so we can run inference on it. See, snapshot writer wrote. Everything's done. See this model? A little off. All right. And here, this model has learn more. So one thing we can do is, I opened that so to make sure that the log is fine. But here we go, checkpoints. And we can actually look at, so you can see train log looks healthy. And this was the iGPU one trained on the conversation, so real conversations. And then this was the exact same one trained on the CUDA. I ended up restarting because if you saw in the video, I ended up putting up the wrong learning rate. And as you can see, this one has learned a lot less. This one as well, I did validation, so it also saves the best validation model. So here we go. Now, first things to do are to plot the training loss. So plot y. And this is the only Python in there just because it has the graphics. Yeah, matplotlib has matplotlib. So we'll plot training loss, and we will grab the directory. All right. Oh wait. Takes the model. Yeah, because it needs the actual equations for the model log, and then we'll do the same thing / train dot. Checkpoints 2. I got fat fingers. There we go. And that gives us the walls and the equations from earlier, which you can see all of those. We'll hit them with the other one. Bid. This is the same model. The same output. All right. And if we, like I said, one of the good things about Kitty is it has a built-in image processor. And there we go. As you can see from our pre-prediction, this model will have a problem going through this band. And we can see that it's able to get through this band and it's coasting, right? Isn't even able to get down to here. Isn't able to get down to here. It's spending quite a bit of time in this layer. And this is 80,000 steps in. So more data, right? Lots of data. That was the wild text, right? The GB2 Climb Max one, which is this random internet data. Well, this one is the one that was trained on real human conversations. Okay. So this was trained on my conversations with Claude, and this is trained on actual dev work. And this was trained on far less, only on 4,000 or 3,000, because they took 1% for the validation. And as we can see, training is going pretty good after 3 epochs. Only 11,000 steps, and it's already picked up the behavior. So in this, we've kind of shown the difference between real data and synthetic data from the exact same model, right? We could give the validation, but at the same point, this model has spent 80,000 steps not learning anything. Well, this model spent 4,000 or 11,000 and is actually doing pretty good. So next, we will CP all the models, copy all the models JSON files to the directory so that we can inference it. Okay. And we'll send the TXT as well. Check. Make sure that we have them in there. We have train PNG and we have the full everything. We're going to go to the directory and we are going to copy the final checkpoint. And we're going to do the same thing. That naming comes from the difference between CUDA and the Vulkan backends. So we'll do CP, we'll do the best model. Okay. Now we have everything we need to inference them. So we can run inference on the untrained model. We get locals, kilometer, whatever. And then we can run it on the checkpoint config. Copy the config, maybe validate. Typos. There you go. Hello, how are you doing today? Boom. Tetyah, blah, blah, blah. Oh, so she did learn. She's beginning to learn. And that was what, 3 epochs? Not too bad. Let's see how the random internet one did. How are you today? How Eastern Gene. It's learned a large distribution. All right. Let's talk to this one using Seraph chat. And you can see here, we load the model. You load the vocab, gives you all the information. And a lot of the stuff in here you'll see are numbered because in reality, it is not very many steps in the actual pipeline. So there's actually 3 steps. Loading the configuration, so you actually have information from the model. Load the tokenizers to be able to do the forward pass, because in inference, you're only doing the forward pass. And then load the full model once you have all the information. Okay. Now we can talk it to it. Again, CB architecture, probably C dev with training name into suite. Okay, so not much. You can see the max tokens were given it allowed, and the temperature is set to 0.7 is a common. I found has been great, really good. As you can tell, it's learned a lot of code, but still within the distribution is it, right? So let's say we passed in a code block to it. Reload. Bash. This is like thinking, right? Dedicated hardware infrastructure embedded before being trained in C. Lua decode or fine. So this model has definitely learned. It's definitely learned something. Okay, that was 1 epoch. Then let's try this one. there is nothing in this model related to what we were saying. Okay. So this model is trained on way more tokens, way more data, and has no logic distribution that's relative to the input that's given to it. Okay. While the one that was trained on real data, smaller amounts of data, was actually semi-coherent and its outputs contained relevance to the actual inputs. So it has a better pre-prediction than the one trained on large amount of data that's all garbage or that's just randomized. Okay. So this point wasn't to make another ChatGPT, because now that you have an actual model, which we can even do that, we can. All right, now let's actually do that. Like we have our own trained version of Qwen in Qwen 3 different versions. And once you have your inference, like, all right, congratulations, you gonna open an AI company? So one of the main things is you can find ways, and I think throughout this actual example, the actual ways of creating these SLMs and stuff isn't just a more data in, better model out. It isn't just a let's do all these funny heuristics. There is a series of steps within each thing to get actual output from a model. And it's all in deterministic, reproducible steps. Loading a model configuration, load a physical model, load the data, build the tokenizer, right? Build the tensor maps, get the actual model response, send the actual forward operations, okay? Now, say we have all our monitors, that's where you load it up. You load your tensor viewer with the model .save tensors. Right. Let's actually do this. So you would load the tensor viewer with model save tensors to see the distribution of your model. You could load it up to be able to compare the two that you just trained, right? The video is already long enough, so I'm going to show you one final thing before we wrap this up. But one of the best things is the gradient snapshot spin, right? So we just had our model, right, that we pre-predicted all the stuff. We just had our model, and now we want to say, hey, why didn't that one model learn? What happened with that model? What's the gradient distribution? What is the issue with, we gave it more data, it's the exact same model, was randomly initialized, right? We're running on an engine that is a one-to-one comparison. We have all the docs that show the comparison, where I've done actual comparisons between them. Right. A bunch of these I've written and made sure that I've kept in order. We need to be able to look inside the model and say, hey, what layers from the model are messed up? What layers are actually causing issues? And that is where the field monitor comes in. So Seraph field monitor, I go in depth into that in another video. It gives us the ability to, while we were training, we could do it live, but we can actually replay the gradients that were going on within the model during training. They're sampled at a harmonic interval, right? And the original inspiration was from Jeff and Minko's retarded time, which I explained in, I think, video 2, and I give the full equation for that. And that basically you can determine the vector speed and the change through observance only in discrete steps. So this is what this is, to sample the tensors during training while they're in an active state of changing at discrete time intervals. And then we can get an assumption of, okay, these are what layers are having issues. So we'll replay that. And here we go. We have our model, all 6 layers. And here, so we have the names for it in layers. And if we play, this is the actual model that trained fine. We can see that there is no hiccups anywhere in this gradient distribution. if we go up here, see the embed layers? Very, very low changes. Okay. Very low changes. You can see it's the embed layer. It's the multi-layer perceptron layer, and we're looking at the input layer norm. So this is the linear scalar layer that you saw in the tensor map. But very, very light changes. So the model was not having any issues. So what does the other model look like? Do we see larger changes in this model? Well, we only got 8 samples. But check that. Much larger. I didn't say much larger, but comparatively visible now. Each layer in the model. So we're seeing this layer is it's easier to see from the side. Isn't much here. But you can see that the input layer norm has a lot more issues. We can see that the post-attention layer, which is this layer, is a lot more. Controls. Which layer is this? Yeah, layer 1's input layer norm as well. But you can see why we have layers, because at each layer, there is less gradient distribution. By layer 1, there's some random ones. But by the time we get to layer 3, stuff's kind of solidified out, if that makes sense. And we can see basically nothing here. Well, the embed layer, I'll have to speed this up for you. So it looks more dramatic. There you go. And those are a lot larger and a lot more noticeable gradients. So there you have your actual gradient distribution, right? So all of this was predicted in our Desmos from the actual layers the model gets stuck at, from our understanding, right? Where it never got down to here, couldn't get through there, right? Well, this one had less information, and look how long it took. It only took about 1 epoch for it to hit this layer, and then when did it exit? At 11,000, right? Or if the validation hit around 8,000. So that layer is where it spent most of its time. Bounced up some, and it keeps trying to bounce through there. So this was the main things I want to show you, just the full training, the full initialization from nothing but an idea and numbers and seeing the actual topology to a trained model, right? Where we can look inside of it, we can view everything we need, we can dump all the information about it, and this is all embedded C. The transformer is doing as it's designed. There's no difference between, or there's no layer between the C code that we create, and then when we compile it and optimize it, and then when we can even open up it and even inspect it. So there is no translation, or there is a translation to binary, but there is no difference between what we write and what gets executed, because it is all being told directly. We're telling the machine, hey, this is the deterministic way to make a stochastic AI, right? And we can choose whatever we want. Like I showed earlier, some of the custom data sets that I made from my own stuff, like the sensor models, like sensor fusion is a big thing, right? And especially microcontrollers. So there's all the other stuff too. Like there's a reinforcement learning environment. Oh my gosh. A reinforcement learning environment where you can load a model and then you can talk to it or whatever and answer questions. So, right. You can do all this stuff. You can load models, convert them. So you have everything you need to make a model. All the experiments, this has been a year worth of experiments. This engine itself was only made in the 6 months started in January, but this has been the year of research into how do these work and why do they function the way they do, and not they're going to take over the world because we need more profit type. Okay. And all this fits under 8 megabytes. All right. So that's what I'm going to leave you all with. That is the end of this video. And if you have any questions, there's my Discord and my Patreon are available, and I'll be dropping more videos, and we will continue to build.